Good day everyone. We are the group 2 and in this video we're going to discuss relation. At the end of this lesson, the learners will be able to first define relation, second identify the special properties of relation, and third form ordered pairs, an arrow diagram, or an equation based on the described relationship shown. What is relation? So it is a subset of A times B. This means that it has two elements. In other words, the relation between two sets is defined as the collection of the ordered pair in which the ordered pair is formed by the object from each other. So we say that if element AB is in relation, we would write X or Y, or X is related to Y. To further understand this topic, let me give an example. So if I have that A is the set containing ABCD and B is the set containing XYZ, then notice it gives me a relation. And the relations are, first, a relation from A to B. So we have AX, BZ, DY, and CX. Next, we have a relation from B to A. So we have XD, YC. Another, we have a relation on B. So we have XX, XY, and XZ. Now keep in mind, it doesn't include all of the ordered pairs like AX, AY, AZ, and so on. Because it's a subset of A times B. Means it could contain all of them, but doesn't have to. So there's different ways that you might see this represented, like digraph. For instance, I have set A containing 1, 2, 3, 4, and its relation is R is equal to 1, 1, 3, 2, 2, 3, 4, 1, and 3, 3. This relation can be drawn as like this. Okay, just follow the direction of arrow. Kung asa ni nagsugod o asa paingon. So first we have 1, 1. So ang arrow niya is like this. From 1, paingon gyapon siya sa 1. Next we have 3, 2. So ang arrow from 3, paingon sa 2. So same process gihapon sa uban. So we have ordered pair 2 and 3. So ang arrow from 2 paingon kay 3. Next is ordered pair 4 and 1. So ang arrow gikan kay 4 paingon kay 1. And lastly 3 and 3. So ang arrow from 3 paingon gihapon kay 3. Now let me give you another example. But in this case, let's start with a digraph and we're going to identify the relation. So here we go. What are we going to do is just follow the direction of the arrow. Kung asa siya nagikan o asa siya paingon. So first arrow, nagikan siya sa A, paingon siya sa A. This means that A is related to A. Next arrow, nagikan siya sa A, paingon sa B. This means that A is related to B. Next, ang arrow is nagikan kay A, paingon kay E. This means that A is related to E. Another arrow, gikan siya kay letter E, paingon siya kay letter B. This means that E is related to B. Next arrow is nagikan siya kay B, paingon kay letter D. This means that B is related to D. Another is, ang arrow gikan kay D, pero paingon gihapon siya kay letter D. So this means that D is related to D. And last arrow, gikan siya kay C, paingon kay letter B. This means that C is related to B. So we see that the relation on A, B, C, D, E is AA, AB, AE, BD, CB, DD, and EB.
Let us proceed to the special properties. There are three special properties. We have reflexive relations, symmetric relations, and transitive relations. But first, let us discuss what is reflexive relation. Reflexive relation is a relation of elements of a set A such that each element of the set is related to itself. In set theory, a binary relation on A is said to be a reflexive relation if every element of the set is related to itself. Let us consider a mathematical example to understand the meaning of this concept. Define a relation on the set of integers z such as 0 is equal to 0, negative 1 is equal to negative 1, 2 is equal to 2, and so on. This implies every integer is related to itself. Hence, the relation is equal to on the set of integers is a reflexive relation.
Symmetric relation. A symmetric relation is a relation R on a set A. If AB belong to R, then BA belong to R. For all A and B belong to A. In other words, we can state that the symmetric property is something where one part is a mirror image or reflection of the other part. Or directly, we can say any picture or frame that can be split into identical halves is termed symmetrical, and each of the divided parts is in symmetrical relation to each other.
Transitive relations are binary relations defined on a set such that if the first element is related to the second element and the second element is related to the third element of the set, then the first element must be related to the third element. A binary relation R defined on a set A is said to be a transitive relation for all A, B, C in A. If A are B and B are C, then A are C. That is, if A is related to B and B is related to C, then A must be related to C. Mathematically, we can write it as a relation R defined on a set A is a transitive relation for all ABC is an element of A. If AB is an element of R and BC is an element of R, then AC is an element of R. For example, if for three elements A, B, C in set A, if A is equal to B and B is equal to C, then A is equal to C. Here, equality is a transitive relation. To understand this transitive relation, let us consider an example of transitive relations. Define a relation R on a set of integers z as A is related to B if and only if A is greater than B. Now, as shown for integers a, b, c in z, A is related to B and B is related to C implies A is greater than B and B is greater than C. We know that for integers, whenever A is greater than B and B is greater than C, we have A is greater than C, which implies A is related to C, that is ARC. Hence, R is a transitive relation. Let us take a look for this example. Check whether it is transitive. Let us define relation R on a set A is equal to 1, 2, 3. Relation is equal to 1, 1, 2, 2, 3, 3, and 1, 2. Here, 1, 2 is an element of R, and 2, 2 is an element of R, and 1, 2 is an element of R. So R is a transitive. As according to the definition of transitive relations, that set A is a transitive relation for all ABC is an element of A if EB is an element of R and BC is an element of R, then EC is an element of R. For R to be transitive, you have to look at every example in the diagram of a path linking three vertices using two lines. Then, you have to check that there is one line linking the endpoints. Example, you have to check that if you can go the long way round, then you can go the direct way. Note that in the definition of transitive, the vertices x, y, and z need not be different.
In example A, relation R on A is defined by R is equals to close and open parenthesis 1 and 1, 1 and 2, and 3 and 3. The relation R is said to be symmetric. If A and B belongs to R, then B and A should be in R. Here 1 and 2 is present in R, but 2 and 1 is not present in R. Therefore, relation R does not satisfy reflexive condition. Therefore, the given relation R is symmetric. Proceed to example B. Given that R is equals to close and open parenthesis 3 and 1, close and open parenthesis 1 and 3, close and open parenthesis 3 and 3, be defined on set A 1, 2, and 3. Close and open parenthesis 1 and 2 element of R. So R is not reflexive. 3 and 1 element of R, 1 and 3 element of R. Hence R is symmetric. Since 3 and 1 element of R, 1 and 3 element of R, but 1 and 1 element of R. Hence R is not transitive.
Example 71. Define R on N by A relation B. If and only if A less than B, then R is transitive. Example 1 less than 2 and 2 less than 3 implies 1 less than 3, but R is not reflexive. Example 1 not relation 1 since 1 is not less than 1, and R is not symmetric. Example 2 relation 3 since 2 less than 3, but 3 is not relation 2 since 3 is not less than 2. Since R is transitive but not reflexive and symmetric, so R is not an equivalence relation to N. Definition: if M n element of Z, we say that M divides N if there exists a element of Z such that M equals MA and write M divide N. So for example, 3 divides 6 since 6 equals 3 times 2, and 3 divides negative 6 since negative 6 equals 3 times negative 2, and also 3 divides 0 since 0 equals 0 times 3. Of course, all integers divide 0 are the same reason. So 0 equals 0 times M for any M element. Suppose that M divide N into M A equals N. Of course, we also assuming that M and N are integer. So we want to prove that M divide N. In order to prove that same number, we need to show that M integer multiplied by A given us by N. We know that 3 divides 6 and 3 divides negative 6 and 3 divides 0. So since the relation divide transitive, which as we just proved, so we must divide by 6. So we can multiply it into 3 times 2 equals 6, and 3 times negative 2 equals negative 6, and 3 times 0 equals 0. So 2 and 0 is our integer, and 3 is our M value, and 6 is our N value. Remember that our proof ended showing that we multiply M by A equals n.
Example 72. Define R and Z by A relation to B. If 3 divides A minus B, this will serve as our formula on defining the relation. And now I'm going to show that R satisfies all three properties, which are the reflexive, symmetric, and transitive. And for our first given example, X element of Z, then by above 3 divides X minus X equals to 0. So X relation to X, therefore R is reflexive. It is reflexive because every object under consideration relates to itself, shows that X relation to X. And for our second given example, X and Y element of Z. If X relation to Y, then 3 divided X minus Y. So 3 divides negative multiplied to X minus Y, then 3 divides Y minus X. So Y relation to X. Therefore, R is symmetric. It is only symmetric if A relating rather to B implies that B relates to A. And for our third given example, X, Y, and Z element of Z. If X relation to Y and Y relation to X, then 3 divides X minus Y and Y minus X. By the definition itself, this means that we can find A and B element of Z such that X minus Y is equal to 3A and Y minus X is equal to 3B. Adding together these two equations, we get X minus Y plus Y minus Z is equal to 3A plus 3B. That is, S minus Z is equal to 3 multiplied to A plus B. Thus, 3 divides X minus 2 and so X is relation to Z. Therefore, R is transitive. It is only transitive if A relates to an object B and B relates to an object C and A relates to C. And by this definition, a relation that satisfies all three properties, which the transitive, symmetric, and reflexive, is called equivalence relation.
A relation that satisfies all the three properties, reflexive, symmetric, and transitive, is called an equivalent relation. As you can see here, the example 73, the 1 and 2 and 3. These are the examples of reflexive, symmetric, and transitive, those are equivalence relation.